Hi guys, and welcome to this, our little jaunt and lesson through completing the square and turning points. Right, we've been dealing with quadratics, which is topic 3 that we are dealing with. And as we have seen here, we've got a recap. So remember that from a previous video or previous lesson, when we have something in the following form, we can find the turning point really easily. Right, and obviously it's called turning point form. We came up with the idea that actually it can be sort of written confusingly in that particular form. This value here is actually a dilation away from the x-axis. The value inside and outside combine to give me my translations both horizontally and vertically, and I suppose I should do that as double arrows. And here is a prime example. So in this situation here, as we say, when seeing this, we can see the turning point of the quadratic equation is 3, 4. So this builds on the idea that we have a standard curve, which is our x squared curve, that goes through 0, 0. It's symmetrical, although my graph doesn't make it look particularly symmetrical. And when we've got a -3 inside the bracket, the convention is that we think of it as the opposite, and so actually the whole graph moves 3 points that way. And then this +4 outside turns it actually into a movement of 4 that way. So if it goes from 0, 0 and it moves 3, 3 along and 4 up, then that is why my turning point becomes 3, 4. Writing things in this format is actually really, really important to us. And what we notice later on, or what we say here, is actually if you think about dilations, doesn't actually change the position or the turning point because it's simply stretching the graph. And if you don't believe me, use that Desmos online calculator and have a go. Do the graph of y equals x squared, do the graph of y equals 2x squared, and see whether the turning point changes. All right? I'm promising you it won't. So now this is the way we actually learn to complete the square. There are a number of ways of doing this, and the way I've always learned, as far as I'm concerned, is one of the best in the world. All right, it certainly makes sense to me to turn it into turning point form. Now, the rules are quite simple. We like the coefficient to be a 1. Now, if that's the case, we only need to look at these first two terms here. And you're going to say why, and I'm going to say to you, well, look at the idea of x plus 2 squared. What happens when I multiply that out? Well, firstly, you do not get x squared plus 4. Anyone who thinks that, stop. When you square something, it is the same as x plus 2 multiplied by x plus 2, which then means that you have to do FOIL, or first times first. That gives me x squared plus 2x plus 2x plus 4, which, when we collect like terms, gives me plus 4x plus 4. Hold on a moment. What do we notice? That's a plus 2 and that's plus 4. So this value inside seems to be half of that one. And just to do another example, if we did x plus 3 all squared, for example, that gives me x squared plus 3x plus 3x plus 9. Move my screen over a little bit, which gives me x squared plus 6x plus 9. What do we notice about that 6 and that 3? They're halfway. So when we have a 1 in front of here, we know that this value here is half of this value here. So I'm now going to write this out as x plus 2 squared. I now have the first part of my completing the square. Remember, we are trying to get it in the form of a x plus or minus something squared plus or minus something else, right? Where this and this are my horizontal and vertical translation. So we've seen that link. Let's make that a proper squared now rather than a 72. But we know that when we multiply this out, we get x squared plus 4x plus 4. Well, we don't actually want a plus 4 here. We want a minus 3. So what we can do is say, right, well, okay, well, if I do x squared, x plus 2 all squared, I want to get rid of this plus 4, and I take away 4 to get rid of this. That now gives me this little bit here, which I now have to take away 3 from to get me to the minus 3 that I want, which, when we simplify it, gives us x plus 2 squared minus 7. Wow! So we've actually now factorized this, or completed the square, and turned it into turning point form. So looking at this now, I know that my turning point is given by -2, -7. Ooh. Again, when we look at this example here, is there a 1 in front of the x squared? Yes. So it means that the value inside the bracket can be half that middle term. Again, when we multiply this out, what do we get? We get x squared minus 3x plus 9, which gives me x squared minus 6x plus 9. Well, the first two parts actually match this here, but I need a minus 10. Well, this has given me plus 9. So what I'm going to do is do x minus 3 squared. If I take away 9, that gives me these first two terms, and then I'm going to take away another 10 to give me the minus 10 that I'm looking for. So we get x minus 3 squared minus 19. And again, looking at this now, I can see that my turning point would be 3, remember it's the opposite of the minus 3, comma, minus 19. Now, when there isn't a 1 in front, as in this particular instance, that's not a major issue. All we need to do is factorize it so that we do get a 1. Now, when you factorize, you're dividing every term by the same thing. And in this situation, I'm going to divide everything on this side by 3. So I'm just going to take 3 outside of a set of brackets. And I get x squared plus 3x minus 4 on 3. Now, I suppose it's at this particular instance where everyone looks at that 4 on 3 and just has some sort of a meltdown and goes, oh my goodness, it is fractions, I can't do fractions. Well, yeah, you can, trust me. Right, this 3 outside now effectively can be ignored. It's not disappeared, it's not removed, it's just that, remember, the way that completing the square works is that if there's a 1 inside of there, it becomes a lot easier. So I'm going to write that 3 outside. I'm now going to put some square brackets. The reason being is that we notice that for turning point form, you get curvy brackets. So x plus, and it's half of this middle term, which is easier to write as 3 over 2 squared. Whoa, fractions, more fractions. Don't worry about it. We can do this. So what happens? If I write x plus 3 on 2 squared, and actually multiply that out, what do I get? I get x squared, I get 3 on 2x, plus 3 on 2x, plus 9 on 4. Now, if you're not sure why, 3 on 2 squared, you square both the top number and the bottom number, which when we add those two together, we get x squared plus 3x plus 9 on 4. Well, that's no good to me, because if you remember, I want the x squared plus the 3x. There's my x squared plus 3x. But I want the last number to be minus 4 on 3, and I currently have 9 on 4. So I'm going to take away the 9 on 4. That gets me back to just this first two terms. And then take away another 4 on 3 to give me what I want. Right, well, that looks like it can be simplified. So minus 9 on 4, minus 4 on 3. Let's put it over a common denominator, because we have to. That's going to be 12. So that's going to give me minus 27, and what's that going to give me? Minus 16, which gives me minus 43 on 12. Now, if you're sitting there having some sort of palpitations about fractions, I'm sorry to say, if you don't get this sorted now with lots of fractions practice, you're going to find methods really, really challenging. And I'm sorry to say it gets harder because algebra starts creeping in with all of this. And whoa, yep, not fun. So that gives me 3 lots of x plus 3 on 2 squared minus 43 on 12. Is that my final answer? No, because I now need to multiply everything up by that 3, which gives me 3x plus 3 on 2 squared minus 43 on 4. Now again, if you don't know why, I've got minus 43 on 12, and I'm timesing that by 3, which is the same as 3 on 1. When you multiply fractions, you multiply the tops together and the bottoms together, but you can also cross-cancel. 3's going there once, and 3 goes into there 4 times, which gives me minus 43 on 4. And ladies and gentlemen, there is my completed the square. Now, when we move on to solving equations, when it's in this form, life is lovely. Because when you solve, remember, you are trying to find where and if these cross the x-axis. And what do we know about that? Well, the x-axis is also known as the line y equals 0, which means that we just make y equal to 0. So x minus 3 squared plus 4 is equal to 0. Take away 4 from both sides and I get x minus 3 squared is equal to minus 4. Get rid of this square root, square by square rooting both sides, and my little alarm bells are starting to ring. Because I get plus or minus the square root of negative 4, if we learn anything in maths, we know that we cannot square root a negative number. We can in specialist maths, but that's a whole new discussion. So actually, in this situation here, because I've got that, this cannot be solved, which would probably suggest, if I was going to find a sketch of this, that actually we know that it would have a crossing point at a minimum at 3, 4. There is 3. There is 4. It's going to be some form of a minimum. Do we notice it doesn't cross the x-axis? Absolutely, that's y. So I suppose if that value there is a positive, the chances are this isn't going to be solved unless there is a negative in front of that graph there, but we'll come back to that later. So looking at this one here, is that negative? Yep, looks like it's going to be solvable. So we get x plus 4 squared minus 3 equals 0 because we're solving. So x plus 4 squared is equal to 3 by adding 3 to both sides. Let's now get rid of that square by making a square root of all sides. X plus 4 is equal to, remember, plus or minus the square root of 3. It's got to be plus or minus because we're looking for 2 solutions. If it crosses, it's going to have those 2 solutions. So x becomes equal to minus 4 plus or minus the square root of 3. And my advice to you is leave it in this form. Do not write it as decimal. It's not needed. All right, decimal, not needed. Right, leave it in third forms. By the time you get to methods 3 and 4, you're going to be writing things in exact form anyway. And looking at this question here, because that's a positive and that's a positive, this is not going to have any solution. Now, remember that a quadratic is actually symmetrical down the center. And it is no surprise that that center point runs through the turning point. So what happens is, we know that axes of symmetries always have an x equals line. All right, I'm trying to think of the right word there. But how does that help as well? If you know what the turning point is, so if we have, for example, y is equal to x minus 3 squared minus 6, then we know that the turning point is equal to 3 comma minus 6. And that means that my axis of symmetry, which is that line that goes through the x coordinate of my bottom point, or my maximum, or my minimum, sorry, is just simply written by x equals 3. Right? So this coordinate here is actually also equal to my axis of symmetry. Now, as I say here, we can do this on the CAS, but what I'm going to do is actually add sort of CAS videos later on, just to highlight some of the best ways of using it, because there are some fabulous functions on the CAS calculators. But for now, ladies and gentlemen, that is how to complete the square and how to find your turning points. I look forward to seeing you, as usual, next time.